After designing and implementing adaptive software services, the next big question is how do we actually integrate with the existing legacy system without everything going on fire? Today, we will cover how to transit from a monolithic application to a fleet of microservices with minimal downtime and risks. We will explore tactics to decouple both the business logic and the data. My name is Derick Chen, and this is Build with DC. Whether you're refactoring a legacy monolith or moving out of a vendor software to a custom-built solution, you will need to transit gracefully and minimize the impact radius of new deployments. As much as you have planned and designed for the new solution, there may always be missing information that nobody knows anymore that will lead to your pager ringing in the middle of the night. If you are a deep sleeper like me, then we need a robust transition plan for the migration. We will go back again to our cafe scenario as an example today to see how we can move from a tightly coupled monolithic application to decentralized services. A quick word on migration prioritization before we dive into the technical details. We should aim to migrate to the modules that has high business value and is the most critically in technical debt. This module might look like this. You have a ton of backlog ticket items for new features and as well as bug fixes. The product team is constantly asking for updates, but it is becoming increasingly difficult to build on this particular module or even to operate it. Your team is spending most of the time trying to put out fires in production instead of actually innovating for new solutions. In other words, with a problem with long time to market for feature implementation and also frequent production issues, modules like this should be the first ones that we look into. In our cafe, the order functionality might be a good example of this. It is highly critical to the business. If there are no orders, there's no revenue. And the tight coupling with other functionalities make it difficult for us to continue developing this module. Even among monolithic applications, there is a varying degree of evil, or tight coupling. Ideally, we should start with what we call a modular monolith. A monolith with an internal structure that aligns with the modules and services we want to split into microservices. It is like when we move houses. The best way is to organize the items and furniture based on which room it should go in the new place. So every module in a modular monolith may be a candidate for future microservice. A good example of a modular monolith would be the implementation of Linux kernel that has modularity with loaded kernel modules, which can extend the capability of the base kernel. With a modular monolith, there are fewer moving parts and higher predictability, allowing us to migrate in stages and realize the benefits of our new adaptive software systems quicker. There's this design pattern called the Strangler Fig, which is named after a type of fern in Australia. The seed of the fern lands on a big tree by the wind, and it starts to grow like a parasite, hijacking nutrients from the host and water, eventually killing the big tree. We will adopt a similar approach with the legacy monolithic system. We will refactor one module at a time till there's nothing left. This can be easily done with a shared API interface that's separately deployed from the monolith. It can act as a request routing platform, much like a switchboard between the old and the new. Initially, all client requests will be routed to the monolith. As we extract the first module into an independently deployed microservice, we then change the API destination of the related requests to point to the microservice instead. The microservice will own its own business logic compute units and as well as transactional data stores. This way, we can incrementally migrate the business processing logic to the new architecture without a big bang approach. Even with the Strangler pattern, you may not be feeling very confident about the first few services that you are refactoring out of the monolith, and that's perfectly normal. You can run both the old and the new for a while during the transitional period until you are certain that the new service that we built is robust and reliable. More on this dual write strategy later. So when can we actually delete the legacy modules that we have migrated out already? Ideally, you should wait until both the business logic compute units and the transactional data are completely decoupled and are operating steadily in the new microservice architecture. In our cafe, This means that we will keep the original monolith running, processing new coffee orders in both systems together for some time. This will indeed incur some additional infrastructure costs, but does give us a chance to ensure that all order-related functionalities are working as expected, to make sure that there is no downtime. But there sure will be some internal dependencies in the application layer. If not, the legacy app won't be called a monolith. For example, there may be other parts of the application that are directly calling functions of the module that is to be moved out soon. Furthermore, it is very likely that the data schema and the structure of the legacy system will differ from the new one. Very often, even modularized monoliths do not have proper data boundaries when it comes to persistence. So we need a translation layer in between to direct existing calls to the new, separately deployed service. This is called an anti-corruption layer. The anti-corruption layer is implemented within the legacy system application layer with the aim of redirecting calls to the original monolith to the new service instead. It should also translate the parameters to the domain model of the new service. We can implement it using the adapter pattern to convert data structures and function calls between the legacy and the new domains. The adapter pattern is essentially a wrapper for the new service interface, similar to how we need a power outlet adapter to plug a device with a US plug into a European outlet. Otherwise, you can also consider event-driven ACL, using event streaming to translate and forward events between systems. These are very useful tactics if you have a highly coupled legacy monolith in business logic that will require significant effort to even modularize. In the adaptive design framework, we tackle the modeling of behaviors and performance of software systems, but we haven't talked about dealing with the existing data. If we were to migrate to microservices in stages, that means we need the data to be consistent in both the old and the new system. If you have an existing modular monolith or have gone through the behavioral design, we have an idea of the data boundaries. If you have yet to go live with the new service, meaning both the legacy system module and the new microservice are operating, you can consider replicating requests to the monolithic system, also to the microservice, to have an initial view of the system performance and behavioral accuracy. One way to do this is to use a transaction outbox. This means that for every request that the legacy monolith handles and writes to the database, we will atomically initiate a duplication request to a new microservice with a separate database table, aka the Outbox. The new service can read from the Outbox table and receive event notifications for new requests, and store the transactional data to its own database. This may be very applicable to the payment service in our cafe. Once an order has been created as a record in the relational database, we will also write it to the Outbox table in the very same transaction. Then, the payment service will read and process payments for these orders from the customer's credit card on file. At the same time, we can keep the monolith alive and check the behavior of the transactions. This way, we're essentially performing a dual write, giving us a chance to inspect the consistency of the new service before switching off the legacy module completely. This is also a great opportunity to implement event sourcing in the new service, which I've covered in the previous video here. Eventually, the legacy system will start consuming and fetching data from the newly deployed services too. Once there are no longer any activity in the original legacy database tables, we can then safely decommission them. As more and more functionality and services are lifted out of the legacy application, we can also start tearing down the anti-corruption layers we have put in place during this transitional phase. And this is the end of the legacy monolith. Sounds nice in theory, but hold on. Do you actually need to completely remove the monolith application? The reason we refactor the new services is to achieve adaptability. Adaptability in implementing new enhancements or scaling up and down to match the incoming traffic. If your remaining monolith is purely in the maintenance mode with no enhancement requests coming from the product team and can handle requests with a high level of cost effectiveness, you may not need to completely decompose the legacy system. not to mention the engineering effort to refactor the monolith, transitioning, and operating the new services. Congratulations! Now you have completed an end-to-end round of adaptive systems design through behavior design, performance design, and finally, the transitional deployment. To build software systems faster and better requires constant design effort. It will not be a big design up front, but rather incremental design on your previous foundations. For future enhancements, you should go through a fast-tracked version of the adaptive systems design process. You should already have the domains with their respective responsibilities and functionalities established. So it's only a matter of adding new product features to the right domain in the right bounded context with high cohesion and loose coupling in mind. Only major changes to the product requirements or significant changes in traffic pattern will require a review of the performance design. So most likely you will not revisit this every sprint. As you can imagine by now, this iterative and additive design process based on a previous foundation will not take much time nor effort at all. I believe this is the key differentiator that can make complex software system projects sustainable and stay adaptive. If you like my videos, please remember to like, comment, and subscribe. I help software engineers build complex systems faster and better. Thank you for joining me today. I'm Derick Chen, and this is Build with DC. See you in the next video.